Now I want to talk about normal subgroups. So this is 3.3 normal subgroups. So suppose you have some group, let's say subgroups, group of symmetries of tetrahedron or something like that. So usually such groups have lots of subgroups of different sizes, and not all of them are equally interesting. So for instance, remember this typical example of a triangle, and then so we had this 2 rotations, identity, 3 symmetries. And if you look, for instance, for subgroups, we have, 3 subgroups which have order 2 generated by these symmetries, and we have a subgroup of rotations. And imagine you just want to describe this subgroup without talking about specific vertices of a triangle. So it's very hard to point into a subgroup of size 2 because there is actually no big difference between them. So there is a subgroup of size 2 which is symmetries with respect to this line, but also there is another one, third one, and they are indistinguishable. Formally speaking, you can switch between them using automorphisms of your group. So let me try to draw it. So for this, I will just draw a lattice of subgroups of S3. So maybe I'm not going to define what is a lattice right now, we will see that later. But if you take this S3, then it has basically one subgroup of order 3. So there is a subgroup containing identity 1, 2, 3, 1, 3, 2. Then it has 3 subgroups of order 2. And these are this identity 1, 2, identity 2, 3, and identity 1, 3. And finally, they all contain trivial subgroup. And if you look at this picture, you'll see that basically this subgroup is very important. This subgroup is very important. This subgroup is very important. They're all unique in a certain sense. And these 3 subgroups are all alike. And the reason is that, remember, we had these automorphisms, for instance, conjugation. And if you start do conjugation, it's the same thing basically as relable vertices. And these 3 subgroups start to get rotated, permuted. This subgroup will always stay in place. And these 2 subgroups will always stay in place. And one of the reasons for that is because you can say what exactly the subgroup is. So there is a description of the subgroup which is avoiding mentioning any triangles. So these are just permutations of sign 1. So, and this is kind of a geometric description, so you don't need to label anything for that, it just has an absolute meaning. It's clear what it is. Kernel of a homomorphism to S2. And so such subgroups which have this property, which are unique, you cannot move them using conjugation, are called normal subgroups. And here is the main proposition. So maybe let me call it theorem. So theorem is as follows. So let G be a group, and we know with some subgroup H. So I'm not going to write down all details. So any group, any subgroup. So and then the following are equivalent. So there are 3 conditions on a subgroup which are all give you the same thing, and in this case we call H normal. So the first one of them is for every G in G, and sorry, G in G, and H, and for every H in H, G, H, G inverse is inside H. So what it says conjugation leaves H fixed. So still elements of H can be permuted by conjugation, but the H as a set is staying fixed, is stable under conjugation. Also people say, so this is what people will say, what people will call invariance. Invariance with respect to conjugation. So This is first condition, which is which gives a condition on H which is called being normal. So second one is so left cosets are the same as right cosets. And the way it's convenient to write it is for every G in G, GH is the same as HG. So here you should be careful. You should remember what this means. These are two subsets of G, so they are both subsets of G, and they are supposed to coincide, meaning have the same elements. So that's really trivial to see that 1 is equivalent to 2. So the fact that 1 is equivalent to 2, so this equivalence is obvious. It's a very simple exercise. So let me leave it as an exercise. Finally, there is a third thing which is equivalent to this 2, and this is less trivial. So there exists a homomorphism from G to some group G prime, let me call it F, such that kernel of F equals to H. By the way, notice that we usually, when we talk about groups, we usually say isomorphic. And here I say equal. And the reason is that I actually mean equal. H is a subgroup of G, and kernel is a subgroup of G. And I mean these two groups coincide. It's absolutely not enough that kernel of F is isomorphic to H as an absolute group. You need H to literally be equal to it. So what it means that basically there is some homomorphism somewhere which takes H and shrinks it to the identity. And so what we have already seen, actually we have seen that 3 implies 1. And this was, I guess, in lecture 2.5 maybe. So we discussed it. And the proof was really simple. Take homomorphism, and you want to show that G, if H is in the kernel, GH inverse is in the kernel, apply F to it, and then it follows from the computation F of G, H, G inverse is equal to F of G, F of H, F of G inverse. And if H is in the kernel, that's identity, and so you get identity. So H is in the kernel, then it implies that GH, G inverse is in the kernel, and so 3 implies 1. And 1 implies 3 we will do next lecture, so this is more interesting. And the reason why it's more interesting because you actually need to construct this group G prime. So the fact that G prime actually exists and there is such a homomorphism, if H is satisfying these properties, it's non-trivial at all. So we will do that, so if H satisfies any of those, then H is called normal. So so these are all definitions of normal subgroup. And also let me maybe say about notation. So notation will be G contains H as a subgroup, and we will make a triangle out of it. So not just a greater or equal sign, but a triangle. And this is the notation for being normal subgroup. So before we go into discussing these homomorphisms, let me give you some examples, and we will just find normal subgroups in certain groups we know, and the fundamental idea is that normal subgroups are the most interesting subgroups, and usually they have the most pretty geometric meaning. For instance, here we have all symmetries of a triangle, and inside we have rotations of a triangle. That's a normal subgroup. Okay, so let's do some examples. So example number 1 is as follows. So if G is abelian, then every subgroup is normal. And that's totally boring because conjugation, so let me formally say X is inside H and G is inside G, then G X G inverse equals G inverse X is X. As simple as that. So abelian groups are not interesting at all. And another example which is trivial is that any group has two normal subgroups which are really easy to find. So every group has a subgroup which is just identity, and every subgroup has a subgroup which is the whole group. And these two subgroups are normal, and I use this triangle here. So, and they are called trivial. So somewhat informally, trivial means they are completely kind of simple. These two examples, they exist for every group. There is nothing that interesting about them. So, and then of course, a very interesting example is we have Sn being permutations, and then it contains as a subgroup An, even permutations. And the reason is that An is actually a kernel of homomorphism, and this homomorphism is sign. So, and we discussed already that if you have a kernel of a homomorphism, it's a normal subgroup. But you can think of it in a different way. So if you have some permutation sigma, and you do tau sigma tau inverse, then the statement is that sine of tau sigma tau inverse equals sine of sigma. And the reason is because, there are various proofs of that. One of them is use multiplicativity of sine, or you can start looking at cyclic structure. No, sine depends only on the number of cycles of different lengths, and these numbers are the same for sigma and tau sigma tau inverse. Okay, maybe a fourth example is the one we already mentioned. So if you take, no, let me do something different. Yeah, okay. One can take G being GLN, F, and then these are matrices, and then one can take H being SLN, F, and I remind you, so we will see these groups more. So these are matrices A, which are inside GLN, such that determinant of A equals to 1, and then this SLN is normal inside GLN F. And the reason is that it's a kernel of a homomorphism given by determinant. So you see, in all our examples, normal subgroup is a kernel of certain homomorphism, and that's actually the case in general. But maybe here is a slightly more interesting example. So one can take, for instance, GL2, and inside you can look at matrices which are lambda, lambda, 0, 0, where lambda is non-zero. So such matrices, they, as one of the homework problems said, is a subgroup isomorphic to F as a multiplicative group. And so these are scalar matrices, and clearly if it's a normal subgroup, because if you take any matrix A and then lambda 0, 0, lambda A inverse, of course you will, so this thing commutes with all matrices. Again, this was a homework problem. And so you get A inverse, you get lambda 0, 0, lambda. So indeed, this subgroup is normal actually. So this is normal. And the question is, okay, is it a kernel of some homomorphism? And the answer is, as we will show, every normal subgroup is a kernel of some homomorphism, but if you want to construct this homomorphism, you need to actually start maybe thinking about projective geometry. This will come later. So if you have a normal subgroup of a group, it's very interesting to think it's a kernel of what, and sometimes it may lead to new groups, new geometry. So the whole reason projective geometry exists from one point of view is that GLN has this normal subgroup. Okay, so now let me give a definition, which is very important. So definition is, so a group G is simple if it has no non-trivial normal subgroups. And this is the most fundamental definition. So a group is called simple if it has no non-trivial normal subgroups. And the whole story of trying to understand and classify finite groups goes usually through, first we try to understand simple groups, and then we try to understand how to build new groups from the simple blocks. And the reason is that if you have a normal subgroups, that it means that you have some homomorphism, and you can sort of sometimes split your question of studying your group into question of studying this homomorphism and its kernel and how they interplay. And that's not easy at all, but clearly the most complicated groups to study from this perspective will be simple groups, because, I mean, there is no way to look at them in a simpler way, simplifying them by looking at some homomorphism from them. And interestingly enough, so we already have seen some examples of simple groups. So example number 6, so I talk about normal subgroups and simple groups at the same time. So Z over PZ is simple. And this is just the statement that, okay, so if it has a subgroup, then we can, let's call it G. We can do this thing with indices. Imagine it has some subgroup identity. And so now, by this I mean strict subgroup. I mentioned it has any strict subgroup. And then we have two indices. And then GH index times H identity index is equal to prime number, which is the order of G being the index of trivial subgroups there. And so either this equals to P, this equals to 1, or the other way around. And so it means G equals to H, or H equal to identity. And so it means that this one is simple. So so this is something which is not very hard to see. So now what I want to, so there will be a homework problem, a long one. It will come in the problem set, which will be next after problem set 3, so problem set 4 probably. And this is actually AN is simple for n greater or equal than 5. So AN even permutations give us a first example of a series of simple groups for every n greater or equal than 5. For n less than 5, something funny happens. We will discuss it. These groups are not simple except for A2 and A3, which are just cyclic groups with 2 and 3 elements. So A4 is not simple. And I can say and n equal to 4, 2 and 3, and 2 and 3 just fall into this case. Sorry, A3 has 3 elements, and A2 is trivial. Yeah, okay, anyways. Okay, so finally in this lecture, I want to look in some more detail in S3, S4, S5, and see what simple subgroups do they have.